If you enjoy calm explorations of big scientific ideas, consider liking the video and subscribing to the channel. And while time quietly keeps moving in its own way, share where you're watching or listening from, whether that is early morning, late at night, or somewhere in between. Time is one of the few things that never needs to introduce itself. From the moment consciousness settles into awareness, time is already there, quietly shaping every experience. It is present in memory, which stores moments that no longer exist. It appears in anticipation, which reaches toward moments that have not yet arrived. It shows up in aging, in routine, in the subtle awareness that mornings feel different from evenings, and that years somehow pass more quickly than childhood summers ever did. Nothing about time feels optional. It feels like a steady background process, always running, always moving forward, whether or not attention is paid to it. Even when nothing particularly interesting is happening, time still seems to pass. Waiting rooms, traffic lights, long nights awake. Time does not stop simply because nothing changes on the surface. This sense of continuity is one of the reasons time feels so obvious. There are no gaps in ordinary experience where time appears to turn off. There is always a sense of before, now, and after. Events seem to arrive from the future, briefly occupy the present, and then disappear into the past. The mind arranges experience into a simple narrative, and time appears to be the thread holding that narrative together. Psychologists have long noted that memory plays a central role in this feeling. The brain is constantly recording recent moments while comparing them to earlier ones. This ongoing comparison creates a sense of movement. Without memory, there would be no clear sense that anything had changed at all. Patients with severe memory loss often describe living in a continuous present, where time feels strangely flattened. The moments still occur, but the sense of flow weakens. Anticipation adds another layer. The brain is always predicting what comes next. Even simple actions rely on this. Reaching for a cup assumes the cup will still be there in the next moment. Walking across a room assumes the floor will continue to exist beneath each step. These predictions give the future a kind of mental presence, even though it has not happened yet. Together, memory and anticipation create the feeling of motion through time. The present feels like a narrow window sliding forward, collecting experiences as it goes. Daily routines reinforce this sensation. Waking up, eating, working, resting. These repeated patterns act like markers, dividing time into manageable segments. Calendars, clocks, and schedules give structure to what might otherwise feel abstract. The ticking of a clock does not create time, but it makes time feel audible, countable, and shared. There is also the body itself, heartbeats, breathing, hunger, fatigue. Biological rhythms quietly track the passage of time even when attention drifts elsewhere. The circadian rhythm, regulated in part by light exposure, keeps the body aligned with the cycle of day and night. When this rhythm is disrupted, as with jet lag or shift work, time can begin to feel distorted. Days blur, nights stretch. This physical response reinforces the idea that time is something real and external, something the body must keep up with. From this perspective, time feels as natural as gravity or temperature. It seems woven directly into reality. And yet even here, subtle cracks begin to appear. Time does not feel the same in every situation. Moments of danger often feel stretched, as though events unfold in slow motion. Periods of intense focus can make hours disappear almost unnoticed. Boredom can make minutes feel unreasonably long, while joy seems to compress entire afternoons into brief flashes of memory. These distortions suggest that the experience of time is not fixed. It depends on attention, emotion, and context. The clock may insist that the same number of seconds have passed, but experience tells a different story. Neuroscience supports this. The brain does not contain a single clock that tracks time uniformly. Instead, multiple systems contribute to time perception, including regions involved in movement, attention, and memory. Time, as experienced, is assembled rather than simply received. Still, none of this seriously challenges the feeling that time itself flows. It merely suggests that perception can bend. The deeper assumption remains untouched. Time feels like something that exists independently of observation, something that continues whether or not anyone is paying attention. Even during sleep, when awareness fades, time is assumed to keep moving. Waking up confirms this assumption. Hours have passed. The world has changed slightly. The sense of continuity is preserved. This is why time feels more fundamental than many other concepts. Space can be left behind by closing a door. Sound can be silenced. Light can be blocked. Time, however, seems impossible to escape. Every thought about anything at all happens within it. Philosophers have long noticed this. William James described the present as having a small but measurable duration, not an instant, but a short stretch in which experience feels unified. This idea fits comfortably with intuition. The present does not feel like a razor-thin boundary. It feels more like a brief holding area where perception, memory, and expectation overlap. None of this requires physics to make sense. It works at the level of experience alone, and that is precisely why time feels so obvious. When something feels this deeply embedded, it rarely invites scrutiny. Air goes unnoticed until breathing becomes difficult. Gravity fades into the background until balance is lost. Time, in the same way, becomes invisible through familiarity. The purpose here is not to undermine that familiarity, but to acknowledge it honestly. Any attempt to understand time through physics has to begin here, with the way time is actually lived. Without this grounding, discussions of relativity, entropy, or cosmology risk feeling abstract and detached. There is also a quiet emotional dimension. Time is tied to change, and change carries meaning, growth, decay, learning, loss. The passing of time is inseparable from the sense that things matter. A world without time would also be a world without stories, without development, without cause leading to effect. This emotional weight further reinforces the feeling that time must be real in the strongest possible sense. Yet history has shown that intuition, no matter how convincing, is not always a reliable guide to the underlying structure of reality. The ground feels flat, but it curves. The sun appears to move across the sky, but it is the earth that turns. Solid objects feel continuous, yet they are mostly empty space. Time may belong to this same category, something deeply familiar, functionally indispensable, and subtly misleading. The question, then, is not whether the experience of time is real. It clearly is. The question is whether the physical universe organizes itself in the same way the mind experiences it. Does time truly flow, or does it only seem to flow because of how memory, prediction, and perception work together? Does physics confirm this everyday picture, gently refine it, or quietly replace it with something far stranger? Those questions sit just beneath the surface of ordinary experience, waiting patiently, much like time itself, for closer attention. Long before equations, laboratories, or even written language, time was already being noticed. Early human societies did not begin with abstract definitions of time. They began with patterns. The most obvious was the sky. The sun rose and set with dependable regularity. The moon changed shape in a slow, repeating rhythm. Stars shifted position across the night sky, returning to familiar arrangements over the course of a year. These cycles were not subtle. They governed light and darkness, warmth and cold, planting and harvest, migration and rest. Time, in this early sense, was inseparable from repetition. A year was not an abstract duration. It was the return of winter after summer, the reappearance of constellations, the moment when rivers swelled or retreated. A day was the alternation between sunlight and darkness. Even shorter intervals were often tied to the body itself. Breathing, heartbeats, hunger, fatigue. Biological rhythms provided a built-in sense of passing moments long before clocks existed. This made time feel deeply embedded in nature rather than imposed upon it. Many early cultures organized their lives around these cycles with remarkable precision. Stone monuments aligned with solstices. Agricultural calendars tracked seasonal shifts closely enough to support entire civilizations. These societies did not measure time by counting seconds or minutes, but by recognizing when the world entered familiar states again. In this framework, time was often circular rather than linear. What had happened before would happen again. Seasons returned. Generations repeated familiar roles. The future was not radically unknown, but patterned after the past. This cyclical view appears in many ancient traditions, from early Mesopotamian calendars to later Hindu and Mesoamerican cosmologies. The idea of time moving steadily forward towards something entirely new was not yet dominant. As philosophy developed, thinkers began to ask deeper questions, not just how to track time, but what time actually was. One of the most influential early attempts came from Aristotle. Rather than treating time as an independent substance, Aristotle argued that time was inseparable from change. In his view, time was a way of describing motion. Without change, there would be no time to speak of. If nothing happened, there would be nothing to measure. This idea had a certain elegance. It aligned well with everyday experience. Time seems to reveal itself through events. A seed becomes a plant. A child grows older. A shadow moves across the ground. Remove change, and time appears to lose its meaning. Aristotle also emphasized that time involved comparison. To say that one event happened before another requires some standard of ordering. In this sense, timekeum was tied not only to motion, but to observation. Someone had to notice that one change occurred earlier and another later. For centuries, this view shaped thinking about time across much of the Western world. Time was not a thing in itself, but a measure of transformation. This approach fit comfortably with the cyclical patterns people observed, and with the limited tools available for investigation. Yet even here, quiet questions remained. If time depends on change, what happens to time when change slows down? Does time pass more slowly during calm periods, and more quickly during chaotic ones? And if no one observes change, does time still exist at all? Philosophical reasoning could explore these questions, but it could not resolve them conclusively. Arguments relied on logic, intuition, and analogy rather than experiment. Different thinkers reached different conclusions, often influenced by metaphysical commitments rather than evidence. This limitation became more apparent as practical needs grew. Navigation across oceans required accurate timekeeping. Knowing longitude depended on comparing local time to a reference point. Astronomy demanded precise predictions of planetary motion. Religious and civic life increasingly relied on coordinated schedules. Informal observations of cycles were no longer sufficient. The problem was not that philosophical ideas about time were wrong, it was that they were incomplete. They described how time appeared, not how it behaved under precise scrutiny. Another tension emerged as societies expanded. Cyclical time worked well for seasons, but human history was becoming less repetitive. Empires rose and fell. Technologies accumulated rather than reset. Written records preserved unique events rather than allowing them to fade into myth. Time began to feel more directional, more historical. This shift did not immediately replace older views, but it added complexity. Time was both repeating and irreversible. Crops returned each year, but people aged only in one direction. Memories accumulated, structures decayed. No season brought youth back. These observations hinted that time might have multiple layers, a repeating surface pattern and a deeper, irreversible progression. Philosophy alone struggled to hold all of this together. What was missing was a way to test ideas about time against the physical world in a controlled, repeatable way. To move beyond description and into explanation, time needed to be measured with increasing precision, detached from specific events and cycles. This did not mean abandoning earlier insights. Cycles, motion, and change would remain central. But they needed to be anchored to something more stable than observation alone. The transition from philosophical time to physical time did not happen overnight. It unfolded gradually as tools improved and questions sharpened. What began as tracking shadows and seasons would eventually lead to pendulums, gears, and eventually atomic transitions. Each step made time less dependent on particular events, and more like a quantity that could be compared across different situations. This shift was transformative. Once time could be measured independently of specific changes, it became possible to ask whether time itself influenced motion, rather than merely describing it. It became possible to compare how time behaved in different locations under different conditions, and eventually at different speeds. But none of that could have happened without the long period in which time was first noticed, named, debated, and woven into human thought without mathematics. Those early ideas, even when incomplete, performed an essential role. They made time a legitimate object of inquiry. They established that time was not just a background assumption, but something worth questioning. The journey toward a physical understanding of time did not begin with equations. It began with people looking at the sky, watching shadows move, feeling their bodies change, and wondering what exactly was passing when nothing else seemed to move at all. That curiosity laid the groundwork for everything that followed. At some point, watching the sky was no longer enough. Shadows still moved, seasons still returned. But as societies grew more complex, the need to divide time into smaller, more reliable pieces became unavoidable. Farming could tolerate rough timing. Trade, travel, and coordination could not. When people needed to meet, sail, pray, or work together, time had to become something that could be shared precisely, not just sensed. This was the quiet beginning of measurement. The earliest timekeeping devices were simple and deeply tied to nature. Sundials tracked the movement of shadows cast by the sun, turning daylight into a readable pattern. As long as the sky was clear, they worked well enough. But clouds erased time. Night erased it completely. Sundials also varied with latitude and season, reminding everyone that time, as measured this way, was local and conditional. Water clocks offered a partial solution. By allowing water to drip at a steady rate, they extended timekeeping beyond daylight hours. Yet even these were imperfect. Water viscosity changes with temperature. Flow rates drift. The clocks worked, but only within limits. What mattered was not perfection, but the growing idea that time could be separated from specific events and tracked continuously. This shift accelerated with mechanical clocks. By the late Middle Ages, gears, weights, and escapements transformed time into something that ticked forward on its own. Bells rang at regular intervals. Hours became standardized within towns. Workdays gained structure. Life began to align itself around the clock rather than the sun. This was more than convenience. It changed how time was understood. When time was marked by mechanical motion, it began to feel uniform. Each tick resembled the last. Unlike seasons or biological rhythms, clock time did not speed up or slow down with circumstance. It imposed regularity on experience even when life itself felt irregular. This uniformity was powerful. It suggested that time itself might flow evenly, independent of what happened within it. One of the first people to seriously explore this idea through experiment was Galileo Galilei. While studying motion in the late 16th and early 17th centuries, Galileo noticed something remarkable about pendulums. Regardless of how wide the swing was, as long as the arc remained small, the time it took to complete each swing stayed nearly the same. This property, known as isochronism, hinted at a natural regularity that could be harnessed. A pendulum did not just mark time, it repeated time. Galileo did not build the first pendulum clock, but his observations laid the groundwork for it. Pendulum clocks, developed later, dramatically improved accuracy. Timekeeping errors shrank from minutes per day to seconds. For the first time, time could be measured finely and consistently over long periods. This improvement had far-reaching consequences. Navigation provides a clear example. Determining latitude had long been possible by observing the stars. Longitude was far more difficult. To know how far east or west a ship had travelled, sailors needed to compare local time with the time at a fixed reference point. Even a small error in timekeeping could translate into massive errors in position, sometimes hundreds of kilometres. The solution required clocks that could survive rough seas while keeping steady time. This challenge drove intense innovation, eventually leading to marine chronometers accurate enough to support global navigation. Timekeeping quite literally reshaped the map of the world. Astronomy benefited just as profoundly. Predicting planetary motion requires precise timing. Eclipses, transits, and orbital periods could only be understood once time was measured consistently. Observatories increasingly relied on clocks rather than naked observation of the sky. Events were no longer simply seen, they were time-stamped. As timekeeping improved, something subtle happened. Time began to feel like a background against which events unfolded, rather than something defined by those events. Clocks did not care whether anything interesting was happening. They ticked on through silence, darkness, and inactivity. This constancy encouraged a new way of thinking. If time could be tracked independently of motion, perhaps time existed independently of motion as well. This idea quietly prepared the ground for classical physics. By the time physics began to formalize laws of motion, time had already been standardized and abstracted. It was treated as a parameter that increased steadily and uniformly, the same everywhere, for everyone. Equations describing falling objects, swinging pendulums, or orbiting planets assumed a single shared time that applied universally. This assumption worked extraordinarily well. With uniform time as a foundation, physics achieved remarkable predictive power. Cannonballs followed calculable paths, planets traced elegant orbits, machines could be designed with confidence. The success of these models reinforced the belief that time itself was stable, neutral, and absolute. Yet it is important to notice what happened conceptually. Clocks did not simply measure time, they defined it. By choosing devices that emphasized regular repetition, society began to equate time with uniform progression. Variations in experience were treated as psychological quirks rather than features of time itself. If the clock said an hour had passed, then an hour had passed regardless of how it felt. This definition was enormously useful, but it was also a choice. The more time was measured this way, the more natural it felt to imagine time as a universal river, flowing at the same rate everywhere. Mechanical regularity became synonymous with temporal truth. There is gentle irony here. The very tools designed to bring clarity also imposed constraints. By relying on clocks built around repeating motion, time was framed as something that repeated perfectly, even though the world itself rarely does. Still, the benefits outweighed the limitations. Measurement enabled comparison. Comparison enabled laws. Laws enabled prediction. Without standardized time, modern science would not exist in anything like its current form. What matters is that this period locked in a powerful assumption. That time could be treated as a single shared quantity, unaffected by who was measuring it or where they were measuring it from. For centuries, nothing seemed to contradict this. Everyday experience matched the clock. Engineering relied on it. Astronomy confirmed it. Time appeared to be the most reliable ingredient in the universe. It took extraordinary circumstances to reveal that this reliability was, in part, an illusion. But before those cracks appeared, measuring time had already transformed it from a lived rhythm into a physical quantity. That transformation made everything else possible, even the discoveries that would later show that time was never quite as simple as the clocks had suggested. By the late 17th century, time had become something that could be trusted. Clocks ticked steadily. Calendars aligned across regions. Astronomical predictions matched observation with impressive reliability. Against this backdrop, Isaac Newton introduced a framework that would dominate science for centuries, not because it was philosophically elegant, but because it worked. At the heart of Newtonian physics was a simple and powerful idea. Time exists independently of everything else. It flows uniformly at the same rate everywhere, whether or not anything happens within it. Motion occurs in time. Forces act over time. But time itself remains untouched by these events. Newton described this as absolute time. It did not depend on motion, observation, or location. It did not care whether an object was moving quickly or slowly, whether it was near Earth or drifting through empty space. Time passed in the same way regardless. This assumption fit perfectly with the tools and experiences of the era. Mechanical clocks reinforced the idea of steady flow. A second followed a second, reliably and predictably. Two clocks placed side by side would remain synchronized. There was no obvious reason to suspect that time behaved differently elsewhere. Everyday experience agreed with the model. What made this idea so powerful was not just its simplicity, but its usefulness. With absolute time in place, motion could be described cleanly. Velocity became distance travelled per unit time. Acceleration became change in velocity per unit time. These definitions allowed complex movements to be broken down into simple, predictable components. Using this framework, Newton formulated the laws of motion and universal gravitation. Falling apples, orbiting planets, swinging pendulums, and rolling cannonballs could all be described using the same set of principles. Time entered every calculation as a shared reference, ticking forward identically for all objects involved. The results were extraordinary. Engineering flourished under these assumptions. Bridges could be built to withstand loads, machines could be designed with predictable performance. Clocks themselves became more accurate through Newtonian analysis of oscillations and forces. Each success reinforced confidence in the underlying picture of time. Astronomy in particular benefited enormously. Planetary motion could be predicted with stunning precision. The return of comets, the timing of eclipses, and the arrangement of the solar system all followed patterns that Newtonian mechanics captured elegantly. Time served as the stable parameter that allowed motion across vast distances to be compared and understood. It is difficult to overstate how convincing this success was. When a theory explains so much so well, there is little incentive to question its foundations. Within this framework, time functioned like a stage. Objects moved across it, forces pushed and pulled upon it. But the stage itself never reacted. It did not bend, stretch, slow down, or speed up. It was simply there, providing a neutral backdrop against which everything else unfolded. This view made time feel passive, important, yes, but not dynamic. In Newtonian physics, space and time were separate entities. Space defined where things were. Time defined when things happened. Neither influenced the other. They were containers rather than participants. This separation aligned neatly with intuition. Space feels like something that can be occupied or left behind. Time feels like something that moves forward regardless. Treating them as independent made sense. There was also a philosophical comfort in this picture. Absolute time offered a universal ordering of events. Everyone, everywhere, shared the same temporal framework. Disagreements about motion or position could be resolved by appealing to this common clock. Even when observers disagreed about where something was, they could still agree on when something happened. This universality helped cement the idea that time was objective in the strongest possible sense, not just experienced similarly, but existing identically for all observers. Importantly, Newton did not claim that absolute time could be directly observed. He distinguished between true time and relative time. Relative time was what clocks measured. True time was the underlying flow that clocks approximated. This distinction allowed the framework to accommodate imperfections in measurement without questioning the concept itself. If clocks disagreed, the fault lay with the instruments, not with time. Once again, the idea proved resilient. For everyday speeds and gravitational conditions, Newtonian time worked flawlessly. Even today, most engineering relies on this framework. Bridges do not collapse because time behaves unexpectedly. Cars do not require relativistic corrections to reach their destinations. For human scales, absolute time remains an excellent approximation. This practical success is important to acknowledge. Newtonian time was not naive. It was extraordinarily effective within its domain. But effectiveness can mask limitations. The framework assumed that time flowed independently of motion, yet motion itself was defined using time. This circular dependence did not cause problems in practice, but it left deeper questions unanswered. Why should time flow uniformly? What determined its rate? Could anything influence it at all? These questions remained largely philosophical for a long time. There were also subtle hints that something might not be quite right. Newtonian mechanics worked best when dealing with objects moving much slower than light. At the time, this was not a concern. Light was poorly understood, and its speed was not yet central to physical theory. As measurements improved, light began to attract more attention. Experiments suggested that its speed was remarkably consistent. Unlike sound or water waves, light did not seem to require a medium that defined a preferred state of rest. This was odd. If time was absolute and space was fixed, then speeds should add straightforwardly. A beam of light emitted from a moving source should travel faster relative to a stationary observer. Yet experiments hinted that this was not the case. At first, these results were treated as curiosities or experimental difficulties. The Newtonian framework was too successful to abandon lightly. When a theory works across centuries and continents, confidence runs deep. And rightly so. The strength of classical mechanics lies in its clarity and scope. It provided a shared language for science, engineering, and astronomy. It unified terrestrial and celestial motion under a single set of rules. It transformed time into a dependable foundation rather than a mystery. But no framework, no matter how successful, is beyond question. The very precision that made Newtonian physics powerful would eventually expose its limits. As measurements became more refined, small discrepancies began to matter. Light, in particular, refused to behave as expected under the assumption of absolute time. For now, though, time remained steady, universal, and unquestioned. It flowed silently beneath every calculation, supporting an entire worldview that treated the universe as orderly, predictable, and fundamentally knowable. That worldview did not disappear overnight. It did not fail catastrophically. Instead, it was gently, almost reluctantly, asked to make room for something stranger. The stage on which physics had played out so confidently was about to reveal that it was not as rigid or as neutral as it had seemed. Imagine a universe where nothing happens. No motion, no change, no stars drifting, no particles colliding, no clocks ticking, no thoughts forming. Everything is perfectly still, frozen in place, not just slowed down, but entirely unmoving. The question is simple, but unsettling. Would time still exist in such a universe? At first glance, it feels like it should. Time, after all, is often imagined as something that flows regardless of events. Even if nothing happens, perhaps time still passes quietly in the background. That idea feels natural, especially after centuries of thinking shaped by clocks and calendars. But this intuition begins to wobble as soon as it is examined more carefully. For Aristotle, time could not exist without change. In his view, time was not an independent ingredient of the universe. It was a way of describing motion. Without movement, there would be nothing to count, nothing to order, nothing to distinguish a before from an after. A frozen universe, in this sense, would also be timeless. This idea aligns closely with experience. Time reveals itself through difference. A sound begins and ends. A shadow shifts. A thought arises and fades. If absolutely nothing changed, there would be no marker to indicate that any interval had passed at all. Newton's view stood in sharp contrast. Absolute time, as he described it, flowed independently of events. Even if the universe were completely still, time would continue advancing at its steady universal rate. Motion happened in time, but time did not depend on motion. Both views feel plausible, depending on where attention is placed. Aristotle's perspective emphasizes observation and comparison. Newton's emphasizes an underlying structure that exists whether or not it is observed. The tension between these views runs deep, and physics has never fully escaped it. Thought experiments make the problem clearer. Consider a universe containing a single particle, floating alone in empty space. Nothing else exists. The particle does not move. There is no background, no reference point, no interaction of any kind. Can it be said that time passes for this particle? If time is defined by change, the answer seems to be no. Nothing changes. There is no way to distinguish one moment from another. The particle has no history, no future, only an eternal sameness. If time is defined independently, then perhaps time passes anyway, but this passing has no consequences. No record, no difference. Time would exist, but it would be unobservable even in principle. Physics tends to be uncomfortable with such situations. Modern physics generally avoids defining quantities that cannot, even in principle, be measured. This is known as an operational definition. A concept is meaningful if there is some way, at least theoretically, to measure or detect it. Time, in practice, is defined by clocks, and clocks require change. A clock is not a mystical object. It is a physical system that undergoes regular, repeatable motion or transition. A swinging pendulum, a vibrating crystal, a transition between energy states in an atom. No change, no clock, no measured time. This does not automatically mean that time cannot exist without motion, but it does mean that physics has no way to access or describe such time. A quantity that leaves no trace and produces no effect falls outside the scope of physical science. This distinction matters. When physics speaks about time, it is almost always speaking about measurable time. Time as tracked by processes, transitions, and interactions. This keeps the discussion grounded, but it also subtly favours Aristotle's intuition over Newton's abstraction. There is another way to approach the problem. Imagine a universe that is almost frozen, but not quite. One tiny process still occurs. Perhaps a single unstable particle decays once every trillion years. Everything else remains unchanged. In this universe, time suddenly becomes meaningful again. That single event provides a reference. Before the decay and after the decay are distinct. Even if nothing else happens, the existence of change anchors time to something observable. This suggests that time, at least as physics handles it, is inseparable from events. Yet the Newtonian idea still lingers because it works so well in practice. Treating time as something that flows uniformly simplifies calculations and matches everyday experience closely enough that the distinction rarely matters. The problem only becomes serious when precision increases. As measurements become more exact, assumptions about time are tested more rigorously. If time truly flows independently, it should behave the same everywhere, under all conditions. If it does not, then the idea of absolute time begins to fracture. This is where the question of motion becomes crucial. If time depends on change, then different kinds of change might produce different experiences of time. If time is independent, then motion should have no effect on how time passes. Physics would soon be forced to confront this directly. Experiments involving light, motion, and precise clocks would reveal that time does not behave as a detached background after all. Instead, it appears to be entangled with motion and interaction in ways that Aristotle might have found familiar and Newton might have found deeply uncomfortable. The thought experiments about frozen universes are not just philosophical curiosities. They sharpen the question that experiments would later answer. Is time something that exists on its own, flowing invisibly even when nothing happens? Or is time a way of describing change, emerging only when the universe gives us something to compare? The answer would not come from introspection or logic alone. It would come from measurement, from pushing clocks to their limits, and from discovering that time itself responds to motion in ways no one had expected. The calm certainty of absolute time was about to face a test it could not pass unchanged. For centuries, light was treated as just another kind of motion. It illuminated objects, warmed surfaces, and revealed the shapes of the world, but it did not seem special in a way that demanded new rules. Like sound, It was assumed to travel through space at some speed relative to its surroundings. If the source moved, the speed should add. If the observer moved, the measured speed should change. This expectation fit neatly within the comfortable framework of absolute time and fixed space. Then the 19th century arrived, bringing precision with it. As instruments improved, scientists began measuring the speed of light more carefully. What they found was surprising. No matter how it was measured, light seemed to move at the same speed. Whether the source was moving or still, whether the observer was approaching or receding, the result stubbornly refused to change. This was deeply unsettling. Under ordinary assumptions, speeds add together. A runner on a moving train runs faster relative to the ground than to the train itself. Sound behaves this way. Water waves do too. Light, according to classical thinking, should be no different. Yet measurements suggested otherwise. Part of the confusion came from a powerful new theory developed by James Clerk Maxwell. In the mid-19th century, Maxwell unified electricity and magnetism into a single framework known as electromagnetic theory. His equations did something remarkable. They predicted the existence of electromagnetic waves, and they predicted their speed. That predicted speed matched the measured speed of light. Even more strangely, the speed emerged from the properties of space itself. It depended on quantities related to electric and magnetic fields, not on the motion of any source or observer. Light, in this description, did not need to be pushed. It simply propagated. This raised an uncomfortable question. If light is a wave, what is it waving in? At the time, waves were understood to require a medium. Sound waves move through air. Water waves move through water. It seemed natural to assume that light moved through some invisible substance filling all of space. This hypothetical medium was called the luminiferous ether. The ether was imagined as perfectly transparent, offering no resistance to motion, yet rigid enough to support extremely fast waves. It was a strange idea, but it allowed physicists to preserve familiar assumptions. Space could remain fixed. Time could remain absolute. Light would simply move through the ether, much like sound moves through air. If the ether existed, then motion through it should be detectable. As the Earth orbited the Sun, it would move through this medium. Light travelling in the direction of a motion should appear slightly slower or faster than light travelling perpendicular to it. The effect would be small but measurable with sufficiently precise instruments. This was the motivation behind one of the most famous experiments in physics. In the late 19th century, Albert Michelson and Edward Morley designed an experiment to detect Earth's motion through the ether. Using an interferometer, they split a beam of light into two paths at right angles, reflected the beams back, and recombined them. If the speed of light differed along the two paths, the interference pattern would shift. The expectation was clear. As the Earth moved, the pattern should change. It did not. Repeated measurements showed no detectable difference. Light travelled at the same speed in all directions, regardless of Earth's motion. The result was not subtle. It was decisive. The ether, as imagined, was nowhere to be found. This outcome created a crisis, though not an immediate one. Physicists are often reluctant to abandon successful frameworks, and for good reason. Newtonian mechanics had earned its authority. Maxwell's equations were working beautifully. The failure lay somewhere in between. Various explanations were proposed. Perhaps objects physically contracted as they moved through the ether, masking the effect. Perhaps clocks slowed down. These ideas were introduced as fixes, not revolutions. They were attempts to preserve absolute time by modifying matter instead. But something deeper was happening. Light was refusing to behave like an ordinary wave. Its speed did not seem to depend on anything external. It did not care how fast the observer was moving. It did not even appear to care about the existence of a medium. This forced a reconsideration of a basic assumption. If the speed of light is the same for all observers, then time cannot be the same for all observers. That statement alone was enough to make generations of physicists uneasy. Under absolute time, simultaneity is universal. Two events either happen at the same time or they do not, and everyone agrees. But if light speed is fixed, then signals used to compare clocks behave differently depending on motion. Events that appear simultaneous to one observer may not appear simultaneous to another. This was not a philosophical quirk, it were a physical consequence. Maxwell's theory demanded a constant speed of light. Experiments confirmed it. Absolute time could not accommodate it without increasingly contrived adjustments. Something had to give. What made this moment so significant was that it did not arise from speculation, but from careful measurement. No one set out to overthrow classical ideas of time. The problem emerged because experiments became precise enough to reveal a mismatch between expectation and reality. Light had quietly exposed a flaw. It is worth pausing to appreciate how radical this was. For centuries, time had been treated as a stable reference. Motion was measured against it. Change unfolded within it. Now, one of the most fundamental phenomena in nature was suggesting that time itself might need revision. The calm certainty of clock time was no longer secure, yet there was also an opportunity here. Maxwell's equations were elegant and powerful. The Michelson-Morley experiment was clear. The data were not ambiguous. A new framework was needed, one that could accommodate constant light speed without abandoning the successes of classical physics. That framework would require a profound shift in perspective. Instead of treating space and time as separate fixed backgrounds, they would need to be considered together. Instead of assuming a universal clock, physics would need to allow time to depend on motion. The cost would be intuition. The reward would be consistency. Light did not merely complicate physics, it clarified something that had been hidden by success. Absolute time worked because most situations did not challenge it. Light did. By refusing to conform, light forced physicists to look more carefully at the assumptions they had inherited. It revealed that time was not as detached, neutral, or universal as it had seemed. The stage was now set for a new way of thinking, one in which time would no longer sit quietly in the background, but take on a more active and surprising role, and all of it began with a simple, stubborn observation. Light moves at the same speed no matter how fast you chase it. In 1905, a quiet recalibration took place. Albert Einstein was not trying to overthrow centuries of physics. He was trying to make sense of a stubborn inconsistency. Maxwell's electromagnetic theory worked beautifully. Experiments confirmed that light moved at a constant speed. Classical mechanics worked beautifully too, but only if time behaved in a very specific way. The two frameworks could not both be entirely correct as they stood. Einstein's solution was deceptively simple. Instead of forcing light to fit into existing ideas about space and time, he adjusted the ideas themselves. He began with two principles. First, the laws of physics are the same for all observers moving at constant speeds relative to one another. Second, the speed of light in empty space is the same for all such observers, regardless of how fast they're moving. These were not philosophical claims. They were statements grounded in experiment. Once accepted, their consequences unfolded with quiet inevitability. If the speed of light is fixed, then measurements of space and time cannot both remain fixed. Something has to give. Einstein showed that it is time, along with space, that must adjust to preserve consistency. One of the first consequences is time dilation. Imagine two identical clocks. One remains still relative to an observer. The other moves rapidly past. According to special relativity, the moving clock ticks more slowly when compared to the stationary one. This is not because the clock is faulty. It is because time itself passes more slowly for the moving system relative to the stationary observer. This effect becomes noticeable only at very high speeds. At everyday velocities it is far too small to detect. But at speeds approaching that of light, it becomes dramatic. This is not an illusion. It is not a trick of perception. It is a real, physical difference in how much time elapses. Another consequence is the relativity of simultaneity. In everyday life, simultaneity feels absolute. Two lightning strikes happen at the same time, or they do not. Everyone agrees. Special relativity shows that this agreement depends on relative motion. Two events that appear simultaneous to one observer may occur at different times according to another observer, moving relative to the first. The disagreement is not due to delayed signals or observational error. It arises from the structure of spacetime itself. This challenges a deeply ingrained intuition. If simultaneity is not universal, then there is no single, shared present that all observers agree on. Each observer carries their own definition of what is happening now, shaped by their state of motion. Time in this framework is no longer a universal river flowing identically everywhere. It becomes personal. This does not mean time is subjective or arbitrary. It follows precise mathematical rules. But it does mean that time depends on motion. Different paths through space correspond to different experiences of duration. Einstein did not arrive at this conclusion lightly. He followed the logic wherever it led, even when it contradicted common sense. The result was a picture of the universe, in which space and time are interwoven into a single structure known as spacetime. In spacetime, distances and durations are not separate entities. They are different aspects of the same underlying geometry. Changing how one is measured affects the other. This shift preserved what mattered most. The speed of light remains constant. The laws of physics remain consistent. The cost is abandoning the idea of absolute time. At first, these ideas seemed abstract, even unsettling, but nature had the final say. Experimental confirmation came from many directions. One of the clearest comes from particle physics. Certain unstable particles created in Earth's upper atmosphere decay extremely quickly when at rest. Yet when they travel toward the surface at high speeds, many more reach the ground than classical physics would predict. According to special relativity, their internal clocks run more slowly due to their motion. Time dilation allows them to survive long enough to be detected. This is not a rare or marginal effect. It is observed routinely in particle accelerators around the world. Another confirmation comes from atomic clocks. These clocks measure time using the frequency of electromagnetic transitions in atoms, providing extraordinary precision. When atomic clocks are placed on fast-moving aircraft or satellites, and compared with identical clocks on the ground, the differences match the predictions of special relativity exactly. The clocks do not malfunction. They record time faithfully. The difference lies in how much time has actually passed for each clock along its journey. This consistency across experiments reinforces an important point. Relativity does not say that time is an illusion. It says that time is physical, measurable, and influenced by motion. What changes is not the existence of time, but its universality. This realization reframes many earlier debates. Aristotle's intuition that time is tied to change finds a new expression. Newton's assumption of a universal background turns out to be an approximation that works only under limited conditions. Special relativity reveals that time is not detached from the physical world. It responds to how objects move through space. There is a gentle elegance in this outcome. Instead of discarding classical physics entirely, relativity contains it. At low speeds, where motion is slow compared to light, relativistic effects become negligible. Time behaves almost exactly as Newton described. The old framework survives as a special case. This layered structure is one of the strengths of modern physics. New theories do not erase old ones. They explain when and why the old ones work. Relativity also reshapes the meaning of duration. Asking how much time passes between two events no longer has a single answer. It depends on the path taken between them. Different observers, following different trajectories, can experience different amounts of time between the same pair of events. This idea feels strange because it undermines a familiar anchor, but it also carries a kind of quiet coherence. Time is no longer something imposed uniformly from outside. It is something experienced along the way. So far, motion has been the key player. Moving clocks run slow. Moving observers disagree about simultaneity. Everything depends on relative velocity. Yet there is another form of motion that has not been addressed. Acceleration. Objects rarely move at constant speed forever. They speed up, slow down, turn and fall. And falling, as it turns out, has something in common with motion through space. Einstein would soon realize that gravity is not a force acting within spacetime, but a feature of spacetime itself. If motion can affect time, then gravity should as well. The implications of this idea would be even more surprising than those of special relativity. Time would not only depend on how fast something moves, but on where it is and how strongly it's pulled. The quiet revision of time had only just begun. Once time is no longer universal, a natural question follows. If different observers experience different amounts of time, whose clock is correct? Relativity answers this by changing the question itself. Instead of asking which clock shows the true time, it asks how much time passes along a particular path through the universe. This leads to the idea known as proper time. Proper time is the time measured by a clock that moves along with an object. It is the time experienced locally, along that object's own journey through space-time. Every physical system carries its own measure of time with it, whether it is a wristwatch, an atomic clock, a beating heart, or a vibrating particle. In this sense, every observer carries a personal clock through the universe. This does not make time subjective or arbitrary. Proper time is precise and well defined. Two observers moving differently will generally accumulate different amounts of proper time between the same events, and both measurements will be correct. This idea resolves many apparent paradoxes. Consider the famous twin scenario. One twin remains on Earth, the other travels through space at high speed and then returns. When they reunite, the travelling twin has aged less. At first glance, this seems contradictory. From the traveller's perspective, could it not be argued that Earth was moving instead? Proper time dissolves the confusion. The key difference lies in the paths taken. The travelling twin follows a path through space-time that involves acceleration and changing direction. The Earth-bound twin follows a simpler path. These paths are not equivalent, and they do not accumulate the same amount of proper time. There is no contradiction because each twin's clock measures the time along their own path. The difference in aging is a direct consequence of those paths being different, not of perspective alone. This is not a thought experiment confined to textbooks. Versions of this effect have been measured using precise atomic clocks. When clocks are flown on aircraft and compared with clocks on the ground, the differences match the predictions of relativity. Each clock records its own proper time faithfully. What matters is not where the clock ends up, but how it gets there. Proper time also clarifies why time dilation is not symmetric in all situations. While two observers moving at constant speed relative to each other can each see the other's clock running slow, situations involving acceleration break this symmetry. Proper time keeps track of the full history, not just relative motion at a single moment. This makes time feel less like a shared background and more like a personal record. Yet it remains deeply physical. Particles, for example, experience proper time as they move through accelerators. Unstable particles decay according to their own internal clocks. When they are moving at high speeds, their decay is delayed relative to laboratory time exactly as special relativity predicts. The particle does not care about external clocks. It decays when its own proper time has elapsed. This perspective brings a quiet shift in how time is understood. Instead of imagining a universal clock ticking for the entire cosmos, it becomes more accurate to imagine countless clocks, each attached to an object, each measuring time along a unique path. These clocks do not disagree in the sense of being wrong. They simply record different durations because they have travelled differently. Relativity, then, does not eliminate time, it personalizes it. There is still structure, there are still rules. Proper time is not free to vary arbitrarily. It is constrained by the geometry of spacetime and by the speed and motion of the object involved. What changes is the idea that time must be the same everywhere. This shift also removes much of the emotional unease that often surrounds relativity. Time does not dissolve into illusion. It remains something that can be measured, predicted, and experienced. It simply refuses to be universal. There is an important subtlety here. Proper time is local. It is what a clock experiences at its own location. It does not require synchronization with distant clocks. In fact, relativity shows that global synchronization is not absolute. Proper time sidesteps this issue entirely by focusing on what is directly measurable. This makes it the most physically meaningful notion of time in relativity. Once this idea is accepted, many earlier puzzles fall into place. Disagreements about simultaneity become less troubling. Different observers slice space-time into moments differently, but each carries a consistent timeline along their own path. The universe, in this view, does not come with a single master timeline. It offers a vast collection of intertwined histories, each with its own measure of duration. So far, this discussion has focused on motion through otherwise flat space-time. Special relativity handles situations where gravity is negligible, and motion is uniform or piecewise uniform. But the universe is rarely so simple. Objects fall, orbits curve, massive bodies distort the paths of other objects. If motion through space-time affects proper time, then gravity, which changes how objects move, must also influence it. This realization opens the door to a deeper revision. Time is not only shaped by how fast something moves, but also by where it moves. The presence of mass and energy alters the structure of space-time itself, changing how proper time accumulates. The clock you carry does not just respond to speed, it responds to gravity, and with that, time steps fully into the geometry of the universe. When gravity enters the story, time changes again. Up to this point, motion has been the main actor. Moving clocks run slow. Different paths through space-time accumulate different amounts of time. Speed shapes duration. But motion alone is not the whole picture. Objects do not simply drift through empty space. They fall, they orbit, they respond to mass. Albert Einstein realized that this could not be treated as a separate problem. If motion affects time and gravity affects motion, then gravity must affect time as well. This insight led to general relativity, a theory that reimagines gravity not as a force pulling objects through space, but as a manifestation of curved spacetime. Mass and energy tell spacetime how to bend. Curved spacetime tells matter how to move, and time is woven directly into that curvature. In general relativity, gravity is no longer something that acts within time, it reshapes time itself. The most immediate consequence is gravitational time dilation. Clocks placed in stronger gravitational fields tick more slowly than clocks placed in weaker ones. A clock closer to a massive object runs behind a clock farther away. This effect is not caused by mechanical strain or environmental damage. It is not a flaw in the clock. It is a difference in how much time actually passes. This happens because gravity alters the structure of spacetime. Near mass, the geometry changes. Paths through spacetime stretch and warp, and proper time accumulates differently depending on location. At first, this sounds abstract, but it has clear, testable consequences. Imagine two identical clocks. One sits on the surface of Earth. The other is placed high above the planet, far from most of Earth's mass. According to general relativity, the clock on the surface runs slightly slower than the one above. The difference is tiny but real. On Earth, the effect amounts to a difference of roughly a few tens of billionths of a second per day between clocks at sea level and clocks far above the planet. This is far too small to notice in daily life, but it is well within the reach of modern instruments. Atomic clocks are precise enough to measure this directly. Experiments conducted by national standards laboratories have placed atomic clocks at different heights and compared their rates. The results match the predictions of general relativity exactly. Clocks at higher altitude tick faster. Clocks deeper in Earth's gravitational field tick more slowly. Time itself responds to gravity. This is not limited to Earth. The effect becomes stronger near more massive objects. Near the surface of a neutron star, for example, time dilation is extreme. A clock there would run dramatically slower than one far away. Near the edge of a black hole, the effect becomes so strong that time appears to slow almost to a halt when viewed from a distance. Importantly, nothing special happens locally. The clock near the massive object ticks normally from its own perspective. Seconds feel like seconds. It is only when compared to clocks elsewhere that the difference becomes apparent. This reinforces a key idea. There is no single, universal rate at which time flows. Time is local. It depends on where you are and how spacetime is shaped around you. One of the most practical confirmations of gravitational time dilation operates quietly every day. The global positioning system relies on satellites orbiting Earth. These satellites carry atomic clocks that must remain synchronized with clocks on the ground. If they did not, navigation errors would accumulate rapidly. The satellites experience two competing effects. Because they are moving quickly relative to Earth's surface, special relativity predicts that their clocks should run slow. Because they are farther from Earth's mass, general relativity predicts that their clocks should run fast. Both effects must be accounted for. When engineers calculate the net result, they find that the gravitational effect is larger than the motion effect. The satellite clocks tick faster than ground-based clocks by several tens of billionths of a second per day. Without correction, this would lead to positioning errors of several kilometers within a single day. The system works because relativity is built into it. This is not a philosophical curiosity. It is an engineering necessity. Navigation depends on understanding that time runs differently at different heights in a gravitational field. What this reveals is profound. Gravity does not merely influence motion, it reshapes the rate at which time itself unfolds. The universe does not provide a single clock ticking everywhere. It offers a landscape of time, where the passage of seconds depends on curvature. This idea replaces the old image of gravity as a pull through space. Instead, objects follow the straightest possible paths through curved spacetime. Those paths determine how much time passes. Time becomes geometric. The closer one is to mass, the steeper the curvature, the slower time accumulates relative to distant regions. Move away from mass, and time speeds up. This is not because time wants to move faster or slower. It is because space-time itself is structured differently. Einstein's equations capture this relationship precisely, linking the distribution of mass and energy to the geometry of space-time. While the mathematics is complex, the core idea is simple. Matter shapes space-time. Space-time shapes time. This also clarifies why gravity and acceleration are so closely related. An observer in a closed box cannot tell the difference between being at rest in a gravitational field and being accelerated through empty space. In both cases, clocks behave the same way. Time dilation appears whenever space-time is curved, whether by mass or by acceleration. This equivalence lies at the heart of general relativity. Once gravity is understood this way, earlier assumptions dissolve quietly. Time is no longer a neutral background. It is an active participant in the structure of the universe. Yet, as before, this does not invalidate everyday experience. On human scales, gravitational time dilation is minuscule. Life unfolds as expected. Meals take the same amount of time. Conversations proceed normally. The differences exist, but they are far below perception. Just as Newtonian time remains an excellent approximation for slow motion, uniform gravity allows time to feel steady and universal. The deeper structure only reveals itself when precision increases or gravity becomes extreme. And that brings attention to environments where gravity is anything but gentle. Dense stars, collapsing cores, and regions where mass is compressed beyond ordinary limits push space-time to its extremes. In these places, time behaves in ways that stretch intuition to its limits. General relativity predicts that near such objects, the flow of time can differ so drastically that comparisons across regions become almost meaningless without careful context. These are not abstract predictions. They are grounded in the same framework that keeps satellites synchronized and experiments consistent. Gravity slows time because gravity reshapes space-time. Time does not merely pass within the universe. It responds to the universe's structure. As gravity grows stronger, the effects become more pronounced, revealing how deeply time is tied to geometry. The calm ticking of clocks hides a remarkable truth. The universe does not share a single tempo, it plays many, all at once. To understand just how far this idea can be taken, it helps to look at the most extreme gravitational environments known. Places where time itself is stretched almost beyond recognition, and there, gravity's influence on time reaches its most dramatic expression. When gravity becomes extreme, time begins to behave in ways that feel almost unreal. Black holes are not special because they are mysterious or destructive, but because they concentrate mass into such a small region that space-time itself is pushed to its limits. They are natural laboratories for testing general relativity, places where the geometry of the universe is stretched as far as it can go without breaking. Near a black hole, gravitational time dilation becomes enormous. As an object approaches a black hole, the gravitational field grows stronger and stronger. According to general relativity, this means that time passes more slowly the closer one gets. A clock near a black hole ticks far more slowly than a clock far away. This effect is not gradual in a gentle sense, it accelerates dramatically. From the perspective of a distant observer, a clock falling toward a black hole appears to slow down more and more. Signals sent outward take longer to arrive. Each tick stretches apart. Light emitted from the clock becomes increasingly red-shifted, losing energy as it climbs out of the intense gravitational well. Eventually, the clock appears to freeze. This apparent freezing occurs at a boundary known as the event horizon. The event horizon is not a physical surface. It is a region of space-time beyond which information cannot escape. Once something crosses this boundary, no signal it sends can ever reach a distant observer. Because of this, the distant observer never sees the clock cross the event horizon. The last signals arrive more and more slowly, fading away as time dilation becomes extreme. From that viewpoint, the crossing never quite happens. This description is precise, but it is also incomplete without another perspective. From the viewpoint of the falling clock itself, nothing special happens at the event horizon, provided the black hole is sufficiently large. The clock ticks normally. Seconds feel like seconds. The laws of physics operate as usual, at least locally. There is no sudden stop in time, no dramatic pause. The event horizon is not marked by a wall or a flash. It is simply a boundary defined by the structure of space-time. This difference between perspectives is not a contradiction. It is a direct consequence of how time and space are shaped near extreme gravity. General relativity allows different observers to experience time differently, and black holes push this allowance to its most dramatic expression. Both descriptions are correct within their own frames. This distinction highlights a crucial point. Time dilation near black holes is not about what happens to objects. It is about how space-time itself is arranged. The extreme curvature changes how paths through space-time accumulate proper time. The falling clock follows a perfectly ordinary path locally. The distant observer's measurements are shaped by the fact that signals must climb out of an increasingly steep gravitational well. Black holes therefore expose the local nature of time more clearly than almost any other object in the universe. There is no single story that applies everywhere. Closer to the black hole, time slows relative to distant regions. Far away, time continues at a different pace. Each clock measures its own proper time honestly. The differences arise because the geometry linking those clocks is severely distorted. This behavior was not invented to explain black holes. It emerges naturally from Einstein's equations. Long before black holes were confirmed observationally, general relativity predicted that sufficiently dense mass would lead to regions from which light could not escape and where time dilation would become extreme. Decades later, observations would catch up. Astronomers have now detected black holes indirectly through their effects on nearby stars, gas and light. Measurements of stellar orbits around supermassive black holes reveal motions that require enormous gravitational influence. Observations of accretion disks show matter heating and emitting radiation in ways consistent with strong relativistic effects, including gravitational redshift. These observations reinforce that the same rules governing clocks on satellites also govern time near black holes. The difference is scale, not principle. What makes black holes particularly valuable is not that they introduce new physics, but that they amplify existing physics. They take the gentle slowing of time experienced near Earth and stretch it toward an extreme. The quiet corrections required for navigation systems become vast separations between clocks. The The everyday truth that time is local becomes impossible to ignore. Black holes also force a careful separation between appearance and experience. From afar, events near a black hole appear to slow and fade. From nearby, events proceed normally. Neither description is privileged. Both are shaped by the geometry of space-time and the path of the observer. This challenges a deeply rooted expectation. There's a strong desire for a single authoritative timeline. Black holes deny that desire. They demonstrate that time is not a global quantity handed out evenly across the universe. It is something accumulated along paths, shaped by gravity and motion. Importantly, this does not mean that time becomes meaningless. On the contrary, it becomes more precise. Proper time remains well defined. The rules governing it remain exact. What disappears is the assumption that time must agree everywhere. Black holes also highlight the limits of intuition. Nothing in everyday experience prepares the mind for situations where time appears to stop for one observer while continuing normally for another. Yet this is not a failure of physics. It is a failure of expectation. General relativity does not promise comfort. It promises consistency. Near black holes, that consistency reveals just how flexible time can be when space-time is pushed to extremes. The familiar idea of a shared present dissolves. What remains is a network of local experiences, each governed by the same underlying rules but unfolding at different rates. These extreme environments serve as a reminder. The universe does not adjust itself to human intuition. Intuition adjusts slowly and imperfectly to the universe. Having seen how time behaves under extreme gravity, it becomes natural to step back and ask broader questions. If time can slow, stretch, and diverge so dramatically, what does that say about its overall structure? Is time something that flows through the universe, or something that simply exists as part of it? Black holes do not answer that question directly, but they make it impossible to ignore. Once time is understood as something that depends on motion and gravity, a deeper question begins to surface. If different observers experience time differently, and if there is no single universal present that everyone agrees on, then what does the universe look like as a whole? Relativity offers a striking answer, not in the form of a new equation, but as a way of interpreting what the equations already say. This view is often called the block universe. In this interpretation, the universe is not something that unfolds moment by moment. Instead, it exists as a complete structure where past, present, and future are all equally real parts of space-time. Events are not constantly coming into being and then vanishing. They are laid out within space-time, much like locations are laid out within space. From this perspective, time does not flow. Rather, consciousness moves along a path through space-time, encountering different events in a particular order. The feeling of passage arises from experience, not from the structure of the universe itself. This idea follows naturally from relativity. If simultaneity depends on the observer, then there is no single slice of the universe that can be called the present. What counts as now for one observer may include events that another observer places in the past or future. Since physics offers no preferred observer, it also offers no preferred present. The block universe takes this seriously. Instead of trying to rescue a universal now, it accepts that all events have their place within space-time. The birth of a star, the formation of a planet, the writing of a thought, and the fading of a memory all occupy distinct regions of the same four-dimensional structure. Nothing needs to move for this to be true. The structure simply exists. This challenges one of the most familiar aspects of experience. The present feels special. It feels like the only moment that is real, with the past gone and the future yet to arrive. The The block universe suggests that this feeling is not a guide to how reality is arranged, but a feature of how minds process information. The present in this view is not a moving boundary, it is a perspective. Each observer traces a path through space-time called a world line. Along that path, events are ordered by proper time. From the inside, this ordering feels like flow. From the outside, it is simply a path through an already existing structure. This does not mean that change is an illusion. Change is encoded in the structure itself. Different points along a world line correspond to different states. A seed at one location becomes a tree at another. The change is real. What disappears is the idea that the universe itself is updating or refreshing. The block universe can be difficult to accept because it clashes with everyday language. Phrases like time passing, moments slipping away, or the future approaching are deeply ingrained. They reflect how experience unfolds, not how space-time is organized. Importantly, the block universe is not a new physical theory. It does not introduce new laws or make new predictions. It is an interpretation of what relativity already implies. Physics itself remains silent on whether time flows. It describes relationships between events, intervals between clocks, and the geometry of space-time. The block universe is one way of making sense of those descriptions. This distinction matters. Accepting the block universe does not require believing that the future is known, predetermined, or fixed in a practical sense. It does not mean that choices are meaningless or that causality is broken. It means that events are ordered within space-time, not created one after another by an external clock. Causality remains intact. Causes still precede effects along world lines. Signals still travel at finite speeds. The structure does not allow paradoxes or backward influence. It simply removes the idea of a universal present that sweeps across reality. Some physicists find this view compelling because it aligns cleanly with relativity. Others find it unsettling because it conflicts with intuition. Both reactions are understandable. There is also room for nuance. The block universe does not deny the psychological experience of time. Memory, anticipation, and attention still create a sense of passage. The brain is not equipped to perceive space-time as a whole. It processes information locally and sequentially. From within that process, the present feels uniquely vivid. This makes the feeling of flow unavoidable, even if it is not fundamental. The idea also helps clarify earlier puzzles. The relativity of simultaneity no longer feels like a problem to be solved. It becomes a natural feature of a universe without a preferred slicing into moments. Different observers simply trace different paths and define different sets of simultaneous events. Black holes, time dilation, and proper time all fit comfortably within this picture. They describe how paths through space-time differ, not how time itself behaves as an independent entity. Still, the block universe leaves an open question hanging quietly in the background. If past and future both exist within space-time, does that mean the future is fixed? This question moves beyond geometry and into interpretation. Physics can describe the structure. It cannot by itself decide how openness, choice, or uncertainty should be understood within that structure. Relativity constrains what can influence what. It does not dictate how events are chosen or determined. Some interpretations suggest that the future is as real as the past, even if it is unknown from within the present. Others emphasize that physical laws describe patterns, not outcomes, leaving room for genuine unpredictability. The block universe does not force a single answer. What it does force is a reconsideration of what it means for something to exist in time. The comfortable image of a spotlight of now moving across an empty future and erasing the past begins to look less like a feature of reality and more like a feature of experience. This realization can feel disorienting, but it can also be quietly calming. If the universe is not rushing forward, then there is no cosmic clock counting down. There is only structure, relation, and the steady accumulation of proper time along countless paths. The question that remains is not whether the future exists in some abstract sense, but how uncertainty, choice, and direction emerge within this timeless structure. That question leads naturally to the problem of time's direction, and why, despite all this symmetry, experience insists on moving one way rather than the other. Once the idea of a block universe is on the table, a question that has been quietly waiting tends to surface. If past and future are both part of space-time, does that mean the future already exists? This question sits at the boundary between physics and philosophy. Physics provides strong constraints, but it does not issue a final verdict. What it does offer is a way to sort different ideas into those that fit comfortably with modern theories and those that struggle. One of the oldest positions is known as presentism. Presentism holds that only the present moment is real. The past no longer exists, and the future does not yet exist. Reality, according to this view, is constantly updating. New moments come into being, while old ones disappear. This aligns very well with everyday experience. The present feels vivid and immediate. The past feels fixed but gone. The future feels open and unreal. Language, memory, and emotion all reinforce this picture. The difficulty arises when presentism is placed alongside relativity. Relativity does not provide a universal definition of the present. Different observers, moving relative to one another, disagree about which events are happening now. There is no single slice of space-time that all observers can agree represents the present moment. If only the present exists, the question becomes unavoidable. Which present? Choosing one observer's present over another introduces a preferred frame of reference. That move breaks a central principle of relativity, which holds that the laws of physics are the same for all observers in uniform motion. For this reason, presentism faces serious tension with modern physics. It is not ruled out logically, but it struggles to coexist cleanly with the structure that relativity describes. Another position, often called eternalism, takes the opposite approach. Eternalism holds that past, present, and future events all exist equally. Nothing is brought into existence or erased as time passes. Instead, all events occupy their own locations within space-time. This view aligns naturally with the block universe interpretation. If space-time is a complete structure, then all events have the same ontological status. They differ only in their location, not in their degree of reality. Eternalism fits comfortably with relativity because it does not require a preferred present. Different observers can disagree about simultaneity without any contradiction about what exists. The cost of eternalism is emotional rather than mathematical. It challenges the deeply felt idea that the future is open in a special way. If future events already exist, it can feel as though choice and novelty are somehow diminished. That feeling, however, does not automatically translate into a physical problem. Physics itself does not assign meaning to existence in this sense. It describes relationships between events, not whether those events feel complete or anticipated. Between these two views sits a third option, often called the growing block model. In the growing block picture, the past and present exist, but the future does not yet exist. The block of space-time grows as time passes. New events are added at the boundary between present and future. This model attempts to preserve the reality of the past while keeping the future open. It appeals to intuition and avoids some of the emotional discomfort of eternalism. However, it faces challenges similar to presentism when combined with relativity. The growing block requires a well-defined boundary between what exists and what does not. Relativity does not provide a universal way to define that boundary. Different observers would disagree about where the block is growing. Once again, physics resists the idea of a single, global present that applies everywhere. What emerges from this comparison is not a clear winner, but a pattern. Views that rely on a universal present struggle to align with relativity. Views that accept all events as part of spacetime align more smoothly with the theory's structure. This does not mean that physics proves eternalism true. It means that eternalism is more naturally compatible with what relativity describes. It is important to keep the boundaries clear. Physics constrains which ideas can coexist with its equations. It does not dictate how those ideas must be interpreted at a human or philosophical level. Relativity tells us that simultaneity is relative. It does not tell us how to feel about the future. There is also a subtle distinction between existence and predictability. Even if future events exist within spacetime, they are not necessarily knowable in advance. Physical laws often describe probabilities rather than outcomes. Quantum mechanics, in particular, introduces genuine unpredictability into many processes. From within the present, the future remains uncertain, regardless of how spacetime is structured. Lack of knowledge and lack of existence are not the same thing. This distinction matters. A book can exist on a shelf even if the ending has not been read. The existence of the final page does not eliminate surprise for the reader. Similarly, the existence of future events in spacetime does not automatically remove openness from experience. Causality remains intact across all these views. Causes precede effects along world lines. Signals do not travel backward in time. Choices still lead to consequences. None of this is threatened by the block universe or eternalism. What changes is the mental image of time itself. Instead of imagining time as something that creates reality moment by moment, physics invites a view in which reality is structured and ordered, with time serving as a dimension that relates events to one another. This shift can feel abstract, but it also removes certain pressures. The universe is not racing toward the future or dragging the past behind it. It simply is, with events connected by relationships that include duration, order, and causality. Still, there is a crucial feature of experience that none of these models fully explains. Even if past and future both exist, experience insists on a direction. Memories point backward. Anticipation points forward. Processes unfold one way rather than the other. Broken objects do not spontaneously reassemble. Aging proceeds in one direction. This directional quality of time remains. Relativity describes the geometry of space-time, but it does not explain why experience is asymmetric. It allows past and future to coexist, but it does not explain why one feels settled and the other feels open. That question lies elsewhere. To understand why time seems to have a direction, it is necessary to look beyond geometry and into statistics, thermodynamics, and the behavior of large systems. The future may or may not exist in the same sense as the past, depending on interpretation. Physics does not settle that question decisively. What physics does make clear is this: whatever time is, its direction is not built into the basic structure of space-time itself. The arrow of time arises from something else entirely, and that is where attention naturally turns next. Despite everything that relativity has revealed, one feature of time remains stubbornly familiar. Time seems to have a direction. Memories point toward the past. Anticipation points toward the future. Causes come before effects. Eggs crack and spill, but they do not leap back into their shells. Smoke spreads through a room, but it never gathers itself back into a neat plume. People age forward, never backward. This one-way character of time is known as the arrow of time. It is not subtle. It shapes experience at every scale, from daily life to the evolution of stars. And yet, when physics looks closely at the fundamental laws governing particles and forces, something surprising appears. Most of those laws do not care which direction time points. If the equations describing motion, electromagnetism or gravity are run backward, they still work. A collision between particles looks just as valid in reverse. A planet tracing its orbit backward obeys the same gravitational rules as one moving forward. Even the equations of quantum mechanics largely allow time to be reversed without contradiction. At the microscopic level, physics is mostly time-symmetric. This creates a deep puzzle. If the basic rules of nature do not distinguish past from future, why does everyday experience insist that they are different? The universe appears to have a preferred direction, but its most fundamental descriptions do not. This tension has occupied physicists for well over a century, and one of the first to confront it directly was Ludwig Boltzmann. Boltzmann worked in the late 19th century, at a time when the atomic nature of matter was still debated. He sought to understand how the smooth laws of thermodynamics, which clearly involve direction, could arise from the reversible motion of countless microscopic particles. Thermodynamics describes systems at large scales. It deals with heat, work, temperature, and equilibrium. One of its central ideas is that certain processes happen spontaneously in one direction, but not the other. Heat flows from hot objects to cold ones. Gases spread out to fill available space. Systems evolve toward equilibrium. This directionality is captured in the concept of entropy. Boltzmann's key insight was that entropy is not a mysterious force or tendency. It is a measure of how many microscopic arrangements correspond to a given macroscopic state. A neatly ordered system can be realized in relatively few microscopic ways. A disordered system can be realized in vastly many ways. The difference in numbers is not small. It is astronomical. Consider a simple example. Imagine a box divided into two halves, with all the gas molecules initially confined to one side. This arrangement is highly ordered. There are many ways for the molecules to be arranged on that side, but far more ways for them to be spread throughout the entire box. If the barrier is removed, the molecules will spread out, not because they are pushed to do so, but because there are overwhelmingly more configurations corresponding to a uniform distribution. The system moves from a less probable state to a more probable one. Entropy increases. Importantly, nothing in the microscopic laws forbids the reverse process. In principle, all the molecules could spontaneously gather back into one half of the box. The laws of motion allow it, but the probability is so vanishingly small that it effectively never happens. This is the statistical nature of the arrow of time. At the level of individual particles, there is no preferred direction. At the level of large collections, probability dominates. Systems almost always evolve toward states that can be realized in more ways. Boltzmann showed that the arrow of time is not built into the laws themselves, but emerges from statistics when dealing with many particles. This explains why macroscopic experience differs so dramatically from microscopic rules. A single collision between two particles can be reversed without issue. A billion collisions occurring in just the right sequence to undo a broken glass is possible in principle, but fantastically unlikely in practice. The universe does not forbid it. It simply never waits long enough. This statistical perspective also clarifies why memory works the way it does. Forming a memory involves creating order. It requires energy, structure, and organization. Memory formation increases entropy elsewhere, typically through heat dissipation. Remembering the past is compatible with the arrow of time. Remembering the future would require entropy to decrease, which does not happen spontaneously. The same applies to information more broadly. Writing, copying, and storing information all involve physical processes that align with increasing entropy overall. The arrow of time, then, is closely tied to the flow of information and energy. Yet there is a subtle and important caveat. Boltzmann's explanation relies on a crucial assumption. The system must begin in a low entropy state. If the universe started in a state of maximum disorder, there would be no direction for entropy to increase, and no arrow of time would emerge. This raises a profound question. Why was the universe ever in a low entropy state to begin with? Boltzmann himself struggled with this. He proposed various ideas, including the possibility that low entropy regions might arise as rare fluctuations within an otherwise high entropy universe. These ideas, while clever, introduced their own problems and paradoxes. Modern cosmology suggests a different picture. Observations indicate that the early universe was remarkably smooth and uniform, corresponding to a very low entropy state relative to what was possible. As the universe expanded and structure formed, entropy increased. Stars ignited, galaxies assembled, and complexity emerged, all while the overall trend toward higher entropy continued. This cosmological beginning sets the direction for everything that follows. The arrow of time we experience appears to be inherited from the initial conditions of the universe. It is not imposed locally. It is carried forward from the earliest moments. This realization reframes the problem. The arrow of time is not a fundamental law written into the equations of motion. It is a global feature of the universe's history. It emerges because the universe started far from equilibrium and has been evolving toward it ever since. Relativity describes the geometry of space-time. It does not explain why entropy increases. Quantum mechanics governs probabilities and amplitudes. It does not impose a direction on time either. The arrow arises when large numbers of degrees of freedom and special initial conditions come together. This also explains why the arrow of time feels so consistent. Every process that involves many particles, from chemical reactions to biological growth, inherits the same direction because they all unfold within the same entropic gradient. There is no competing arrow pulling the other way. The past feels fixed because it is associated with lower entropy states that have already evolved. The future feels open because it contains many possible higher entropy configurations. This does not mean the future is unstructured or random. Constraints, laws, and probabilities still apply. But the number of possible future states vastly exceeds the number of possible past states compatible with the present. The arrow of time is therefore not about inevitability. It is about likelihood. This statistical origin also explains why the arrow is so robust. Small fluctuations do not reverse it. Local decreases in entropy can occur, but they are always compensated by larger increases elsewhere. The overall direction remains unchanged. Understanding the arrow of time requires letting go of the idea that direction must be fundamental. Instead, it emerges from simplicity giving way to complexity, from order giving way to multiplicity. The universe does not push time forward. It unfolds in a way that makes backward unfolding overwhelmingly unlikely. This realization quietly resolves a long-standing tension. The laws of physics can be time-symmetric, while experience remains time-directed. Both can be true because they operate at different levels. What remains is to understand entropy itself more carefully. to see how it is defined, measured, and applied across physical systems. The arrow of time points forward because entropy does, and to understand why entropy behaves the way it does, it helps to look more closely at what entropy actually is. Entropy is often described as disorder, but that word can be misleading. A better way to think about entropy is as a measure of how energy is spread out and how many microscopic arrangements correspond to what we see at a larger scale. It is not about messiness in a visual sense. It is about probability. When entropy increases, energy becomes more evenly distributed, and systems move towards states that can be realized in vastly more ways. This statistical perspective is the key to understanding irreversibility. Consider a simple everyday example. A drop of ink falls into a glass of water. At first, the ink is concentrated in a small region. Over time, it spreads out until the color is evenly distributed throughout the glass. The water never spontaneously clears itself, leaving the ink neatly reassembled into a single drop. Nothing prevents this reversal in principle. The microscopic laws governing the motion of the ink molecules allow it, yet it does not happen. The reason is not a force pushing the ink outward. It is probability. There are relatively few microscopic arrangements that correspond to all the ink molecules being confined to one small region. There are astronomically many arrangements in which they are spread throughout the glass. As the molecules move randomly, the system almost inevitably drifts toward the overwhelmingly more probable state. Entropy increases because probability favors it. The same reasoning applies to breaking. When a glass falls and shatters, the fragments scatter across the floor. Reassembling the glass would require every fragment to return to exactly the right position, with the right orientation and speed. The laws of motion do not forbid this. But the number of microscopic conditions required is so specific that the chance of it happening spontaneously is effectively zero. Irreversibility emerges not because nature dislikes order, but because ordered states occupy an infinitesimally small region of possibility compared to disordered ones. This is why irreversibility feels absolute in daily life. Once energy is dispersed, it does not conveniently reconcentrate. Once structures are broken down, they do not reassemble themselves. Heat flows from hot objects to cold ones, not because heat prefers cold, but because energy spreading out is statistically favored. Entropy provides the arrow, but probability provides the reason. It is important to emphasize that entropy increase is not guaranteed in the sense of a law enforced by force. It is guaranteed in the sense that rolling 1 trillion dice will almost certainly produce an average result. Extreme deviations are possible, but they are so unlikely that they can be ignored for all practical purposes. This distinction matters. When a system contains only a few particles, entropy fluctuations are noticeable. In very small systems, energy can spontaneously concentrate for brief moments. In large systems, involving trillions upon trillions of particles, fluctuations become vanishingly rare. Macroscopic irreversibility is a numbers game. This statistical reasoning also explains why entropy increase is time-directed. If a system starts in a low entropy state, almost every microscopic evolution available to it leads toward higher entropy. The reverse paths exist, but they form an unimaginably small subset of possibilities. The system does not know which way is forward in time. It simply explores what is available. Probability does the rest. This is why entropy is so closely tied to the arrow of time. Entropy does not increase because time moves forward. Time appears to move forward because entropy increases. Energy dispersal gives time its direction. This perspective also dissolves certain misconceptions. Entropy does not mean decay or chaos in a moral sense. It does not mean that everything becomes useless or broken. Entropy increase allows complexity to arise. Stars burn by dispersing energy. Life exists by maintaining local order while exporting entropy to the environment. The universe becomes more interesting as entropy increases, not less. What entropy forbids is not structure, but free reversal. Once energy has been spread across many degrees of freedom, gathering it back requires an extraordinary coincidence. The more degrees of freedom involved, the less likely that coincidence becomes. This statistical irreversibility applies everywhere. Chemical reactions proceed toward equilibrium. Pressure differences equalize. Temperature gradients smooth out. Even social processes like mixing crowds or distributing resources often follow similar probabilistic patterns, though governed by different rules. Physics provides the underlying explanation. Entropy also clarifies why memories point backward rather than forward. Creating and storing a memory involves a physical process that increases entropy overall. Remembering the past aligns with entropy increase. Remembering the future would require entropy to decrease, which does not occur spontaneously. The same logic applies to records of any kind. Photographs, fossils, written documents, all are traces left by processes that increase entropy. The past leaves evidence. The future does not, because it has not yet undergone the processes that would generate those traces. Irreversibility is therefore not a mystery layered on top of physics. It is a natural consequence of statistics applied to large systems. Yet this explanation contains a quiet assumption. Entropy can only increase if the system starts in a low entropy state. If everything were already maximally dispersed, there would be nowhere for entropy to go. No direction would emerge. No arrow would form. This brings attention back to the beginning. The fact that entropy increases today implies that entropy was lower yesterday, and the day before that, and earlier still. Tracing this logic backward leads to a striking conclusion. The universe must have started in an exceptionally low entropy state. This is not a small claim, given the vast number of possible configurations available to matter and energy. The early universe appears to have occupied a very special arrangement. Smooth, uniform, and far from equilibrium, it provided the conditions necessary for entropy to increase over cosmic time. Why this was the case is not fully understood. Physics can describe how entropy evolves. It can calculate probabilities and predict trends. What it cannot yet explain is why the initial conditions of the universe were so finely poised to allow a long arrow of time to unfold. This question does not undermine the explanation of irreversibility. It deepens it. Entropy explains why processes run one way rather than the other. It explains why the future feels open and the past feels fixed. But it also points to an earlier mystery, one that lies at the origin of the universe itself. The arrow of time, so familiar and so reliable, rests on a foundation that was laid long before stars formed or atoms combined. Understanding that foundation requires stepping back even further, toward the earliest moments of cosmic history. Entropy tells us how time gets its direction. The remaining question is why the universe was set up to allow that direction to exist at all. At this point, it might seem that time's direction is absolute and unavoidable. Eggs break, heat spreads, memories accumulate, everything points one way. And yet, in laboratories around the world, physicists routinely work with equations that make no distinction at all between past and future. Run them forward, and they work. Run them backward, and they work just as well. This is not a loophole or a trick. It is a genuine feature of many of the fundamental laws of physics. Take classical mechanics. The equations describing how objects move under forces remain valid if time is reversed. A ball rolling down a hill obeys the same rules as a ball rolling back up, provided the initial conditions are adjusted accordingly. The mathematics itself does not care which direction time points. The same is true for electromagnetism. The equations governing electric and magnetic fields allow solutions that move forward or backward in time without contradiction. Even much of quantum mechanics shares this symmetry. The basic equations remain unchanged if time is reversed. This raises an intriguing possibility. If the laws allow time reversal, can time actually be reversed in practice? In carefully controlled situations, the answer is yes, at least in a limited sense. Physicists routinely create systems where the evolution can be effectively reversed. In some experiments, particles are guided through sequences of interactions and then driven back along nearly the same path. In others, wave patterns are recorded and then played backward, reconstructing their original form. One striking example comes from studies of waves in complex environments. By carefully recording how a wave spreads through a medium and then sending a precisely reverse signal back through the same system, researchers can cause the wave to retrace its steps, refocusing on its original source. This has been demonstrated with sound waves, electromagnetic waves, and even quantum wave functions under specific conditions. From the outside, it can look like time running backward. In computer simulations, this reversal is even clearer. A simulated system of particles can be evolved forward in time and then reversed by changing the sign of time in the equations. The particles retrace their trajectories perfectly, as if nothing irreversible had occurred. These demonstrations are not illusions. They reflect the genuine time symmetry of the underlying laws. So why does this not contradict everyday irreversibility? The answer lies in scale, control, and information. In laboratory reversals, the systems involved are small, isolated, and exquisitely controlled. Every relevant detail is tracked or constrained. Energy loss is minimized. External influences are carefully excluded. Under these conditions, reversing the evolution is possible. Everyday systems are nothing like this. A cup of coffee cooling on a table interacts with trillions upon trillions of particles in the surrounding air, the table, the room, and the wider environment. Every collision, vibration, and radiation exchange carries information away. To reverse the process, every one of those interactions would need to be precisely undone. The equations allow it. Reality does not provide the opportunity. This is why reversibility is scale-dependent. At the level of a few particles or well-isolated waves, reversibility can be demonstrated. At the level of macroscopic objects interacting with their environment, irreversibility dominates completely. The difference is not in the laws, it is in the number of degrees of freedom involved. As systems grow larger, the number of microscopic details that would need to be controlled grows beyond reach. Entropy increases, information disperses, and the probability of spontaneous reversal collapses to effectively zero. Time symmetry survives in principle, but not in practice. This distinction helps resolve a common confusion. The existence of reversible experiments does not undermine the arrow of time, it explains it. The arrow emerges when systems are large, complex, and open. Reversibility appears when systems are small, simple, and closed. Both behaviors arise from the same underlying rules. There is also an important conceptual lesson here. Irreversibility is not enforced by a hidden switch in the laws of physics. It emerges from the overwhelming imbalance between the number of ways a system can move toward disorder versus the number of ways it can move back toward order. Reversing time requires precision. Letting time run forward requires none. This asymmetry explains why time reversal is fragile. The slightest error, The tiniest interaction with the environment destroys the delicate conditions needed for reversal. Once information is lost into uncontrolled degrees of freedom, the path back is effectively erased. These experiments also clarify why the arrow of time cannot be understood by looking only at local laws. The equations governing motion, fields and particles are blind to direction. They do not encode past or future. The arrow arises from boundary conditions, from how systems are prepared, and from how many degrees of freedom are involved. This brings the discussion back to the largest system of all, the universe itself. If small systems can be reversed when prepared carefully, and large systems cannot, then the arrow of time at cosmic scales must depend on how the universe as a whole was prepared. The universe appears to have begun in an extraordinarily special state, low entropy, highly ordered, far from equilibrium. From that starting point, irreversible processes could unfold naturally, without requiring any time asymmetric laws. Every star that forms, every planet that cools, every memory that is written inherits its direction from that initial condition. Laboratory reversals, rather than challenging this picture, reinforce it. They show that time symmetry is real at the microscopic level, and that the arrow is something layered on top, emerging only when complexity and scale come into play. This layered view of time is one of the quiet achievements of modern physics. The universe does not forbid time reversal. It simply makes it unimaginably unlikely once systems grow large and interconnected. So when time appears to run backward in an experiment, it is not breaking the rules, it is revealing them. The arrow of time is not written into the equations, it is written into the way the universe began. To understand why that beginning was so special, it is necessary to step back even further, beyond laboratories and experiments, and toward the earliest moments of cosmic history. Only there does the full story of time's direction begin to take shape. To understand why time has a direction at all, it is necessary to look backward as far as current science allows. Every explanation of the arrow of time eventually points to the same place, the beginning of the universe. Modern cosmology describes the universe as having expanded from an extremely hot, dense state. This framework is commonly called the Big Bang. It is not a claim about an explosion in space, but a description of space itself expanding and cooling over time. As the universe expanded, energy spread out, structures formed, and complexity emerged. What matters most for time's arrow is not the expansion alone, but the state the universe began in. Surprisingly, the early universe appears to have been a low-entropy state. At first, this sounds counterintuitive. The early universe was hot, dense, and energetic. It might seem chaotic. But entropy is not simply about temperature or energy. It is about how that energy is arranged and how many microscopic configurations are possible. The early universe was remarkably smooth and uniform. Matter and energy were distributed almost evenly, with only tiny variations in density. This smoothness represents a very special configuration. There were far fewer ways for the universe to be arranged in that state than in the clumpy, structured universe seen today. In other words, despite its intensity, the early universe was highly ordered. As the universe expanded, gravity amplified tiny differences. Regions slightly denser than average pulled in more matter. Stars formed, galaxies assembled, black holes emerged. These processes increased entropy dramatically, even as local structures became more complex. This is one of the great insights of modern cosmology. Entropy increases not because everything becomes uniform, but because gravity allows energy to spread into more and more possible arrangements. A smooth universe has low gravitational entropy. A universe filled with stars, galaxies, and black holes has much higher entropy. The arrow of time follows this progression. The fact that entropy has been increasing ever since the earliest moments implies that the universe began in an extraordinarily low entropy state. This initial condition set the direction for everything that followed. Every cooling star, every chemical reaction, every biological process inherits its direction from that beginning. This realization reframes the arrow of time. Time does not point forward because of local laws alone. It points forward because the universe started far from equilibrium and has been moving toward it ever since. Initial conditions matter. If the universe had begun in a high entropy state, there would be no arrow of time, no preferred direction, no irreversible processes. The laws of physics would still operate, but nothing would distinguish past from future. That is not the universe we observe. Instead, the universe began in a state that made entropy increase not only possible, but inevitable. The arrow of time was not written into the equations, it was written into the starting point. This raises a natural and difficult question. Why did the universe begin in such a special state? Here, the confidence of explanation gives way to humility. Cosmology can describe the early universe with remarkable precision. Observations of the cosmic microwave background show tiny temperature variations that match predictions of early expansion models. Measurements of large-scale structure trace how matter clumped over billions of years. These observations strongly support the picture of an expanding universe evolving from a hot, dense, low-entropy beginning. What they do not yet explain is why that beginning had such low entropy. Several ideas have been proposed. Some involve inflation, a brief period of extremely rapid expansion that could smooth out irregularities. Others suggest deeper principles that constrain initial conditions. Some speculate about multiverses or selection effects. None of these ideas are confirmed. At present, there is no widely accepted explanation for why the universe started in such an ordered state. This is not a failure of physics, it is a boundary. Science progresses by identifying patterns, building models, and testing predictions. When it reaches a point where multiple explanations fit the available data, it pauses. The low-entropy beginning is one such point. What matters is recognizing what is known and what is not. It is known that the early universe was low entropy. It is known that this condition explains the arrow of time observed today. It is not yet known why this condition held. This honesty is part of what gives the explanation its strength. Rather than inventing an answer, physics marks the limit of understanding and waits for further insight. The arrow of time, then, is not a local feature. It is a global one. It stretches from the earliest moments of cosmic history through every process unfolding today. Each clock ticking forward, each memory forming, each system evolving toward equilibrium is participating in a trend set billions of years ago. Time's direction is inherited, not imposed. This perspective also softens certain intuitions. The arrow of time is not pushing the universe forward. The universe is not being driven by time. Instead, the universe is unfolding from a special beginning, and time reflects that unfolding. Expansion plays a central role in this story. As space expands, energy spreads. As energy spreads, entropy increases. As entropy increases, processes acquire direction. The growth of space provides room for the arrow of time to operate. Without expansion, entropy would have far fewer pathways to increase. With expansion, the number of possible configurations multiplies dramatically. Time, entropy, and expansion are deeply linked. This does not mean time is caused by expansion. but it does mean that the structure of the universe at large scales shapes how time behaves at every scale. From the cooling of the cosmic background to the metabolism of living cells, the same directional trend applies. Understanding time's arrow therefore requires thinking cosmologically. It requires accepting that some features of reality depend not only on laws, but on how those laws were instantiated at the beginning. The universe did not start in a random state. It started in a special one. Why it did so remains one of the deepest open questions in physics. What is clear is that time's direction is not an accident of human perception. It is a reflection of cosmic history. To place time fully within this expanding universe, it is necessary to understand how cosmic expansion itself shapes the meaning of time and how time is measured and compared across vast distances. That is where attention naturally turns next. Time takes on a different character when viewed at the scale of the entire universe. On everyday scales, time feels personal and local. Clocks tick, lives unfold, years pass one after another. But when attention expands to billions of years and billions of light years, time becomes something that links vast regions of space into a shared history. This broader perspective is captured by the idea of cosmic time. Cosmic time is not the time measured by any single clock or observer. It is a way of describing the overall evolution of the universe, based on its large-scale structure. In this view, the universe has a shared timeline that traces how it has expanded, cooled, and changed since its earliest moments. This idea emerged from observation rather than philosophy. In the early 20th century, astronomers began to notice something unexpected. Distant galaxies were not sitting still. Their light was shifted toward longer wavelengths, indicating that they were moving away. The farther away a galaxy was, the faster it appeared to be receding. Edwin Hubble was among those who carefully documented this pattern. His observations showed a clear relationship between distance and recession speed. The universe was expanding. This discovery transformed the meaning of time in cosmology. If space itself is expanding, then looking farther into space also means looking backward in time. Light from distant galaxies takes millions or billions of years to reach us. Observing them reveals how the universe looked long ago. Time and space become inseparable at this scale. Cosmic time allows astronomers to describe the age of the universe, the formation of structures, and the sequence of major events. It provides a way to say that stars formed after the universe cooled, that galaxies assembled over billions of years, and that planets emerged long after the first light was released. This is not the same as a universal clock ticking everywhere. It is a coordinate system that works because, on the largest scales, the universe appears remarkably uniform. Galaxies are distributed evenly when averaged over vast distances. The expansion looks the same in all directions. This large-scale uniformity makes cosmic time meaningful. It allows physicists to speak about an early universe, a middle age, and a far future, even though local experiences of time differ due to motion and gravity. Deep time enters naturally here. Human history spans thousands of years. Recorded civilization covers a few thousand more. Geological processes stretch over millions of years. Stellar lifetimes extend into billions. Cosmic evolution unfolds over timescales that dwarf all of these. Against this backdrop, human experience occupies an almost vanishingly thin slice. The sun has been shining for billions of years and will continue for billions more. Galaxies collide and merge over periods longer than complex life has existed on Earth. Even the formation of atoms occurred hundreds of thousands of years after the universe began. Cosmic time reveals how small and brief individual moments truly are. Yet it also provides context. The same arrow of time that governs daily life governs cosmic history. Entropy increases, structures form and evolve, energy spreads out. Expansion provides room for this unfolding to continue. The expansion of the universe plays a crucial role in shaping deep time. As space expands, matter thins out, temperatures drop, new physical processes become possible. Early on, the universe was too hot for atoms to exist. Later, atoms formed. Still later, stars ignited. Expansion set the stage for each transition. Time, in this sense, is not just duration, it is opportunity. Different eras of the universe allow different kinds of complexity. Time marks not just how long things last, but when they can happen at all. This perspective also tempers certain intuitions. It is tempting to imagine the universe aging in the same way a person does, gradually wearing down. In reality, cosmic time is not a single trajectory toward decay. While entropy increases overall, complexity can rise locally for long periods. Galaxies form, stars shine, life emerges. These processes are enabled by expansion, not suppressed by it. Cosmic time, therefore, has layers. There is the steady march toward equilibrium, and there are long stretches where structure and novelty flourish within that march. Placing human life within this framework can feel unsettling or comforting, depending on perspective. On one hand, individual lives are fleeting. On the other, they are part of a story that spans billions of years and connects every atom to the earliest moments of the universe. Time at this scale is less about urgency and more about continuity. The universe does not rush, it unfolds. This view also reinforces a key theme. There is no single notion of time that applies at all scales in the same way. Proper time governs individual paths. Gravitational time dilation shapes local rates. Cosmic time describes the overall evolution of spacetime itself. Each is valid within its domain. Physics uses whichever description best fits the question being asked. There is no need to force them into a single intuitive picture. As attention shifts toward the smallest scales, another tension emerges. Cosmology describes time smoothly, as a parameter that tracks expansion and change. Quantum physics, by contrast, treats time very differently. In many quantum theories, time is not something that evolves dynamically in the same way space does. It enters as a background parameter, not an observable. This mismatch becomes increasingly important when trying to understand the earliest moments of the universe, where quantum effects and gravity must both be considered. Cosmic time works well once the universe is large and smooth. It becomes harder to define when space-time itself is subject to quantum uncertainty. The same universe that looks orderly at large scales becomes strange and probabilistic at small ones. Understanding time fully requires navigating both perspectives. From the vast expansion traced by galaxies to the fleeting interactions of particles, time appears in different roles. Connecting these roles remains one of the central challenges of modern physics. The story of time does not end with cosmic expansion. It becomes more subtle. To see why, it is necessary to turn toward the quantum world, where time behaves in ways that are less intuitive still, and where its role in the laws of nature is far from settled. By the early 20th century, physics had split into two remarkably successful frameworks. Relativity described space, time, gravity, and the large-scale structure of the universe with extraordinary accuracy. Quantum mechanics described atoms, particles, and the microscopic world with equal success. Each worked beautifully within its domain, and yet they treated time very differently. This difference sits at the heart of some of the deepest unresolved problems in physics. Quantum mechanics emerged from attempts to understand phenomena that classical physics could not explain. The behavior of atoms, the emission of light, and the stability of matter all demanded a new framework. Thinkers like Niels Bohr and Werner Heisenberg helped shape a theory that was precise, predictive, and deeply counterintuitive. In this theory, physical systems are described by mathematical objects that encode probabilities rather than definite outcomes. Measurements do not simply reveal pre-existing properties, they play an active role in determining results. But while space, position, momentum, and energy appear as quantities that can be measured and uncertain, time occupies a strange position. In most formulations of quantum mechanics, time is not treated as an observable at all. Instead, time appears as an external parameter. It is something that labels how a system changes, but it is not something the system itself possesses in the same way it possesses energy or position. The equations describe how the state of a system evolves with respect to time, but time itself remains outside the system. This is a subtle but important distinction. In relativity, time is part of spacetime. It can stretch, slow, and differ from place to place. It is dynamical. In quantum mechanics, time is fixed and universal. It does not fluctuate. It does not become uncertain. It simply ticks in the background. This mismatch creates tension. At the quantum level, many quantities are subject to uncertainty. Position and momentum cannot both be precisely known at the same time. Energy and duration are linked in similar ways. Yet time itself is not placed on equal footing with other observables. This asymmetry has long puzzled physicists. Why should space coordinates be operators, subject to quantum uncertainty, while time remains a classical parameter? Why does quantum mechanics treat time as something absolute, when relativity shows that time is relative? The answer is not settled. Historically, this treatment of time emerged because it worked. Early quantum theories were built to explain experiments, not to resolve philosophical consistency. Using time as a background parameter allowed accurate predictions of atomic spectra, chemical behavior, and particle interactions. The success was overwhelming. But as physics pushed toward deeper questions, the cracks became harder to ignore. Consider how measurement works in quantum mechanics. A quantum system evolves smoothly over time according to precise rules. Then, when a measurement occurs, the system appears to jump into a definite state. This jump is not described as a gradual process in time. It is treated as instantaneous. This creates discomfort. If time is fundamental and continuous, what does it mean for something to happen instantaneously? If time is relative and observer-dependent, whose time governs the jump? These questions do not arise in simple laboratory calculations, but they loom in attempts to unify quantum mechanics with relativity. There is also the problem of clocks. In quantum theory, clocks are physical systems. They're made of atoms and particles, and therefore should obey quantum rules. Yet time itself is assumed to be classical and exact. This creates a circular situation. Quantum systems evolve in time, but time is measured by quantum systems. At some point, this separation becomes questionable. Efforts to address this have led to various proposals. Some approaches attempt to define time relationally, using one physical system as a clock for another. Others explore formulations where time emerges from correlations between quantum states, rather than existing independently. None of these approaches has yet become standard. The tension becomes even sharper when gravity enters the picture. General relativity makes time dynamical. Space-time responds to matter and energy. Clocks tick at different rates depending on gravity and motion. Time is part of the physical fabric of the universe. Quantum mechanics, in contrast, assumes a fixed background time that does not respond to anything. Trying to combine these frameworks leads to profound difficulty. In attempts to formulate a quantum theory of gravity, time often disappears entirely from the fundamental equations. The resulting descriptions are timeless in a literal sense. They describe relationships between configurations without reference to an external time parameter. This creates what is sometimes called the problem of time. If the fundamental description of the universe does not include time, how does time emerge? How does change occur? How do clocks tick? These questions are not philosophical distractions. They arise directly from trying to apply quantum principles to spacetime itself. Different approaches offer different answers. Some suggest that time emerges only at large scales, much like temperature or pressure. Others propose that time is real but must be redefined in quantum terms. Still others suggest that time, as commonly understood, is not fundamental at all. What unites these ideas is uncertainty. There is no consensus solution. Quantum mechanics works extraordinarily well without resolving this issue. Relativity works extraordinarily well within its domain. The conflict only becomes unavoidable when both are pushed to their extremes. This situation is unusual in physics. Normally, when two successful theories conflict, experiments guide the way forward. In this case, the relevant regimes involve energies and scales far beyond current experimental reach. The earliest moments of the universe, the interiors of black holes, conditions where quantum effects and gravity are equally strong. Direct tests are not yet possible. As a result, the role of time in quantum theory remains unsettled. It is clear that treating time as a simple background parameter is inadequate for a complete description of reality. It is equally clear that removing time entirely creates conceptual challenges that are not yet resolved. This leaves physics in an uncomfortable but productive position. Time is essential to experience. It is essential to thermodynamics. It is essential to cosmology. And yet at the deepest theoretical level its status is unclear. This uncertainty invites a broader question. Is time a fundamental ingredient of the universe, or is it something that emerges from deeper, timeless laws? The answer may not be simple. It may involve multiple layers, where time appears differently depending on scale and context. What feels continuous and flowing at human scales may be approximate, arising from statistical and relational effects. Quantum mechanics does not yet tell a complete story about time. It hints that time may not belong at the deepest level in the way space and matter do. Whether this hint points toward a profound revision or a subtle reformulation remains an open question. What is clear is that understanding time fully requires confronting this quantum problem head-on. The universe at its smallest scales does not obviously come equipped with a ticking clock, and that raises the possibility that time, so familiar and so central, may not be as fundamental as it seems. By this point, time no longer looks like a simple backdrop. It slows with motion. It bends near mass. It fragments into personal histories. It emerges from entropy. It becomes difficult to locate cleanly within quantum theory. All of this naturally leads to a deeper question. Is time fundamental, or does it arise from something more basic? This question sits at the frontier of theoretical physics, particularly in efforts to reconcile quantum mechanics with gravity. In these efforts, time often behaves in unexpected ways, sometimes fading from the equations entirely. One prominent line of thought suggests that time is not a basic ingredient of reality, but an emergent one. In this view, time appears only at certain scales, much like temperature or pressure. Temperature feels fundamental in daily life, yet it does not exist at the level of individual particles. It emerges statistically from their collective behavior. Time, some physicists suggest, may be similar. Several approaches to quantum gravity explore this possibility. One such approach is loop quantum gravity, a framework that attempts to describe spacetime itself as quantized. In this picture, space is not smooth and continuous, but composed of tiny discrete units woven together into a network. These networks evolve according to rules that do not rely on an external time parameter. Physicists such as Carlo Rovelli have explored the idea that time, as ordinarily understood, does not appear in the most fundamental description. Instead, physics is written in terms of relationships between variables. Change exists, but not with respect to a universal clock. From this perspective, time is something inferred from correlations. One physical system changes relative to another. One process can be used to track another. What is called time is a convenient way of organizing these relationships, not a separate entity flowing underneath them. This idea is often described as relational time. Rather than asking what time is doing, the theory asks how systems change relative to each other. A clock is just one more physical system. Its readings gain meaning only when compared with other processes. This is a radical shift from everyday thinking. It suggests that time is not something the universe has, but something the universe does, in a relational sense. Time emerges when enough structure exists for change to be ordered and compared. Other approaches reach similar conclusions through different routes. In some formulations of quantum gravity, the fundamental equations describe a static structure. There is no time variable at all. The universe, at its deepest level, appears frozen. Change re-enters only when certain degrees of freedom are treated as clocks for others. This leads to what is sometimes called a timeless fundamental description. It is important to be clear about what this does and does not mean. It does not mean that nothing happens. It does not mean that experience is an illusion. It means that the language used to describe the most basic layer of reality may not include time in the way higher-level descriptions do. Time in this sense would be emergent. This idea is speculative, but it is not arbitrary. It arises because attempts to combine general relativity and quantum mechanics repeatedly run into trouble when time is treated as fundamental. Removing time from the deepest equations can resolve certain inconsistencies at the cost of intuition. That cost is significant. Human experience is saturated with time. Memory, anticipation, and causation all depend on it. Any proposal that removes time from the foundation must also explain how such a vivid feature of experience arises so reliably. This is where caution is essential. No current theory has demonstrated conclusively that time is emergent. Loop quantum gravity remains incomplete. Other approaches, such as string theory, treat time differently and often retain it as a fundamental parameter. There is no consensus. What exists instead is a landscape of ideas, constrained by mathematics, guided by consistency, and limited by the absence of direct experimental tests. The scales at which quantum gravity effects become significant are far beyond present reach. They involve energies and distances associated with the earliest moments of the universe, or the interiors of black holes. Observational access is indirect at best. As a result, these ideas remain provisional. Physics is careful here. Speculation is allowed, but it is labelled clearly. Emergent time is a possibility, not a conclusion. What can be said with confidence is this: time behaves very differently depending on scale. At human scales, it flows smoothly and relentlessly. At relativistic scales, it bends and diverges. At quantum scales, its role becomes ambiguous. This pattern suggests that time may not be a single, simple concept. It may be layered. At some levels, time functions as a useful parameter. At others, it may dissolve into relationships. At still others, it may re-emerge statistically, tied to entropy and information flow. This layered view helps reconcile conflicting descriptions without forcing them into a single mold. It also reframes the original question. Asking whether time is fundamental may be less useful than asking where time applies and why. Some features of reality may require time for their description. Others may not. The universe may not come equipped with one master clock. Instead, clocks may arise wherever stable processes allow duration to be tracked. From this angle, time looks less like a universal substance and more like an organizing principle that becomes meaningful under certain conditions. This perspective also returns attention to perception. Regardless of its ultimate status, time is experienced. The brain orders events. It builds narratives. It distinguishes before from after. Any physical account of time must ultimately account for why experience has this structure. Whether time is fundamental or emergent, its role in shaping consciousness cannot be ignored. And that brings the discussion back to a familiar place. After exploring time as geometry, entropy, probability, and speculation, the final step is to look at time as it is lived. Not as an equation or a coordinate, but as a feature of awareness. Whatever time turns out to be at the deepest level, it is through perception that it becomes meaningful, and it is there, in experience itself, that the story of time quietly comes full circle. After everything physics has revealed, a quiet truth remains. Time feels like it flows. It feels as though there is a moving present, sliding steadily forward, carrying experience along with it. Moments arrive, linger briefly, and then fall away into memory. This sensation is so familiar that it often feels inseparable from time itself. Yet physics has shown that time does not flow in the way this feeling suggests. So where does the feeling come from? The answer lies not in spacetime alone, but in the way living systems process information. The sense of temporal flow emerges from the interaction between physics, biology, and the brain. At the most basic level, experience is built from change. The nervous system is a physical system embedded in the same universe described by thermodynamics. It operates far from equilibrium, consuming energy and exporting entropy. Every neural signal, every thought, every memory formation is a physical process that follows the arrow of time. The brain does not passively observe time. It constructs a sense of time from how information is received, stored, and updated. Memory plays a central role. Memories are records of past states. They are physical traces, encoded in neural connections, chemical changes, and electrical patterns. Creating and maintaining these traces requires energy and increases entropy elsewhere. This makes memory formation inherently time-directed. Memories point backward because they are formed by processes that leave records. The future has no records yet, not because it does not exist in some deeper sense, but because the physical processes that would encode it have not occurred. This asymmetry alone goes a long way toward explaining the feeling of flow. At any given moment, the brain has access to a rich archive of past information and almost no information about what comes next. The present feels vivid because it is where new information is arriving and being integrated. The past feels settled because it is stored. The future feels open because it is not. Anticipation complements memory. Brains are prediction machines. They constantly generate expectations about what is likely to happen next based on past experience. These predictions are updated as new information arrives. This ongoing comparison between expectation and input creates a sense of motion through time. Experience feels dynamic because it is continuously being revised. Importantly, this process does not require time itself to move. It requires only that information arrives in a particular order, and that records accumulate in one direction. That direction is provided by entropy. Neural processes are irreversible. Once a signal has passed and a memory has been updated, returning the brain to its exact previous state would require reversing an enormous number of microscopic interactions. The laws of physics allow this in principle, but the probability is effectively zero. The brain therefore experiences time as irreversible, because it is built from irreversible processes. This perspective also explains why the present feels special. The present is not a moving point in space-time. It is the set of processes currently being integrated by the brain. Sensory input arrives, predictions are adjusted, memories are formed, attention is focused. The present is a window of integration, not a universal moment. Different species experience this window differently. Some animals integrate information over very short timescales, others integrate over longer ones. Humans typically experience the present as spanning a few seconds, a duration shaped by neural processing rather than by physics. This shows that the felt present is not a fundamental feature of time, it is a biological construct. Neuroscience reinforces this view. Studies of perception show that the brain does not process information instantaneously. Signals take time to travel. Different sensory inputs are integrated over short delays. The experience of a unified now is the result of synchronization, not simultaneity. What feels immediate is already slightly in the past. Yet this does not undermine experience, it explains it. The brain stitches together information into a coherent narrative because doing so is useful. It allows organisms to act, learn, and survive. The sense of flow is part of that narrative. Physics does not deny this experience. Instead, it shows that experience operates at a different level of description. Physical time describes relationships between events. Psychological time describes how those events are processed by conscious systems. These descriptions are compatible. Relativity allows different observers to experience different amounts of time. Biology explains how organisms experience those amounts. Thermodynamics explains why experience has a direction. None of these perspectives cancel the others. They fit together. The feeling of flow does not need to be elevated to a fundamental feature of the universe to be real. Pain is real without being a fundamental force. Color is real without being an intrinsic property of light. Time flowing can be real as an experience without being a property of space-time itself. This distinction is often uncomfortable because it feels like a downgrade, but it is not. Understanding that the feeling of flow arises from physical and biological processes does not make it less meaningful. It makes it intelligible. It also resolves a long-standing tension. Physics does not need to explain why time feels like it flows by forcing flow into its equations. Biology and neuroscience already explain why systems like brains experience ordered change the way they do. Conversely, experience does not need to dictate the structure of the universe. The universe is free to be stranger than intuition, while still giving rise to familiar sensations within it. This layered understanding is one of the quiet strengths of science. It allows multiple truths to coexist at different levels. Time can be a dimension in space-time. It can be a parameter in equations. It can be a statistical arrow. It can be an emergent relational quantity, and it can be a felt sense of passage. None of these need to exclude the others. When these layers are kept distinct, much confusion dissolves. The universe does not rush forward. Spacetime does not update itself. Past and future do not compete for reality. At the same time, experience unfolds, memories accumulate, and anticipation reaches forward. Time feels like it flows because living systems are built to register change in one direction. That direction was set by the low entropy beginning of the universe. It is maintained by irreversible physical processes. It's interpreted by biological systems that depend on memory and prediction. From the outside, time may look static or geometric. From the inside, it feels alive. Both views are true within their domains, and in recognizing that, something subtle happens. The mystery of time does not vanish, but it softens. It becomes less about contradiction, and more about perspective. Less about choosing which view is correct, and more about understanding how different views connect. Time does not need to flow for experience to feel meaningful. Meaning arises because experience unfolds moment by moment, along paths shaped by physics, biology, and history. The universe provides the structure, life provides the feeling, and somewhere between the two, time becomes something both deeply strange and quietly familiar, not because it moves, but because change is noticed, remembered, and expected. That noticing is where time, as it is lived, gently comes into being. Time begins as a feeling. It feels steady, familiar, always present. It seems to carry moments forward, arranging experience into a before and an after. For most of human history, that feeling was enough. Time was measured by shadows, seasons, and heartbeats, and it appeared to flow in a simple, reliable way. Physics has shown that this simplicity is only one layer. When time is measured carefully, it stretches and compresses. It slows with motion. It slows with gravity. It separates into personal histories rather than a single shared clock. At the larger scales, it becomes part of cosmic expansion. At the smallest, its role becomes uncertain, even elusive. And yet none of this removes time from the world. Clocks still tick. Causes still precede effects. Memories still form. Entropy still increases. The arrow of time remains steady, not because it is written into every equation, but because the universe began in a special state and has been unfolding ever since. Physics can say some things clearly. It can say that there is no universal present. That time is local, that duration depends on motion and gravity, that irreversibility arises from probability, not force, that the future is uncertain in practice, even if space-time itself may be structured. It can also say where its answers stop. It cannot yet explain why the universe began with such low entropy. It cannot yet fully reconcile time in quantum mechanics with time in relativity. It cannot yet say whether time is fundamental or emergent at the deepest level. These are not failures, they are boundaries. Science advances not by eliminating mystery, but by placing it carefully, separating what is known from what remains open. Time, it turns out, lives partly in each category. What becomes clear is that intuition and physics are not enemies. The feeling that time flows is real as an experience. It arises from memory, anticipation, and irreversible processes in the brain. Physics does not need to deny this feeling to explain the universe. It simply places it at the right level. Likewise, physics does not need to match intuition exactly to be meaningful. The universe is allowed to be strange, layered, and larger than immediate experience. Understanding grows not by forcing agreement, but by seeing how different descriptions fit together. Time does not rush. The universe does not hurry. There is no cosmic countdown. There is structure. There is change. There is order giving way to possibility. Every moment exists within a vast framework shaped by gravity, motion, probability, and history. Within that framework, experience unfolds gently, one memory at a time. Nothing needs to be fixed or settled for this to be comforting. Time can be understood quietly, as something measured, something experienced, something constrained by laws and shaped by beginnings, as something that does not demand urgency, but invites perspective. The universe has room for patience. Whatever time ultimately is, it has carried everything to where it is now, and it will continue, in whatever form it takes, without needing to flow, rush, or resolve itself completely. Being within time is not a problem to solve. It is simply where understanding happens.